Hello. Welcome to my first ever video. What I'm really hoping to do here is just give a completely open and honest and insightful perspective from a real practicing industry engineer who's also still fairly young and has, as meaningful of a connection as possible to, what it was like to be in school. I'm not far off from that. And so I'm hoping I can just give a perspective back and shed some light on how you might be feeling as an engineering student, what you can expect going forward and into the workplace or farther into your studies and research. And to be fair, I'm a little bit biased. There's going to be a heavy flavor into my field of study, which won't necessarily make itself apparent until we get really deep into this. So I'm going to start, really basic, EE 101, very, very, very fundamental stuff that, depending on how far along you are in your schooling, this may or may not be relevant to you or helpful. But, you got to start somewhere. And I think, given that this is my first ever video, first ever time trying to do this teaching thing, we'll see. We'll grow together along the way. So I think what I'm going to do is start with really an overview of, I guess, what am I going to teach? Like, I want to teach circuits is my specialty, my area of interest, and it's what you would learn in a real EE 101 course. I mean, maybe we should call this EE 101. Maybe that's too vague, or maybe this is coming too soon, because I'm trying to think of, what should I really start with here? I mean, the first thing I want to say is, what is a circuit? I mean, maybe that's a good starting point. Like, if you don't already know coming into this, like, what are we talking about? I could just start with an example. And I think the most canonical one, a really common starting point would be like a car headlight system. Maybe that makes sense. So, and what I'm going to do as I go into this, I'm going to draw things. I'm going to draw symbols that may or may not make any sense. You're not going to know what they are, and I will get to them. But, like I said before, I got to start somewhere. So, what to do? Well, let's say, okay, and you're going to have to excuse my handwriting here. Let's say you have a car. Oh yeah, that's going to work. Yeah. Oh my god, this is embarrassing. This is the part we really care about, the front of the car here. Okay. So basically, yeah, alright. You got headlights here. And now imagine each of those lights is connected to the battery under the hood. Now it might look something like this. A line runs to the headlights and connects to both of them like this. Runs around to the other electronics under the hood and then connects back to the battery. So as an engineer, the way I might describe this circuit in a form that we call a schematic might be something like this. And I'm wondering, looking at my camera, I can't see exactly how big this is, but in any case, let's look like this. Okay. Now what the hell is this? What are the rules? What rules am I playing by here? And I'll get to that, I promise. But first, let me just explain how this works. So this is a voltage source. Now this could be many, many things. In this case, it's a battery, right? And it creates a voltage. And this is a switch. When it closes, there will be current that flows through this circuit. And it flows through, these lines I've drawn are describing the wires. They don't have to be wires, right? Like, these lines just mean that these things are connected. And this little squiggle here and this squiggle here, each one of these is a headlight, right? And so what happens is You would close this switch when you turn on your car, or when you flick the headlight button. You close it, and then all of a sudden current flows from this source or battery through these things right here that represent the headlights. And in general terms, what I've drawn here is the symbol for a resistor. And I'll get more to that. But at its nature, what this is a source of voltage or power or current or whatever you want to say, and then you have a load, quote unquote, in these resistors. Now, it's kind of a tangent. You wouldn't actually see a system like this in a modern car. This is kind of dated, mechanical in nature like this, with the switches and the fact that these are even run on the same parallel circuit like this. But that's neither here nor there. The point of this is just to describe an example of a circuit, and what am I talking about in the most general terms when I say a circuit? Like, what's involved? And I think then the most natural thing, I've given kind of this hand-wavy example, I think then the most natural thing from here would be to say, well, what's a circuit? How do we define that? And I think, well, let me write this down. Okay, so a definition of the word circuit, and in particular I'm talking about electrical circuits. This is even more vague than that. I mean, I could stick the word electric before the word circuit. Yeah, I mean, it doesn't get much more general than this. Okay, I've used the word circuit in its own definition, right? So then I think what's going to have to come next is I'm going to define, well, what's a circuit element, right? And it could be, again, anything. Really, the meat of the definition here is that it's a closed path. Really, the physical phenomenon that these physical objects are experiencing is the flow of electric current. One of the most basic tenets of electronics and circuits that you'll learn is that in order for electric current to flow, there must be a closed path. Current doesn't just travel from point A to point B. Current circulates through a circuit. I know I have this kind of circular definition where I'm not really telling you what a circuit element is, and therefore almost not really telling you what a circuit is, but I could put anything here. Like, for the sake of argument and generality, let's just say this is anything connected in a closed loop, and you don't even have to have conductors. Like I was saying, the real meat here is that it's a closed loop, and there's a circulation of sorts. You could have oftentimes people make the analogy between electric current and fluid flow of any kind, and I think it's really a good one, and maybe I'll talk about it a little bit because it does help understanding in the beginning. But in any case, I will come back to this because it's really important, and I'll definitely dedicate an entire episode to this, probably several, but I don't think right now is the correct moment. I think what's most important now is for me to talk about electric current, or just introduce the idea. So let's get to that. What is an electric current? Well, electric current, it's the time rate of flow of electric charge through a circuit or circuit elements. And now here we go. I keep using this word circuit elements. It seems like we're not getting anywhere, but we are going somewhere, albeit slowly. So what did we learn here? An electric current is a time rate. It's a rate with respect to time of the flow of electric charge. Okay, some new terminology there. And yeah, that charge is flowing through the circuit or circuit elements. So really, when we say electric current, we're talking about the flow of electric charge. And now we've finally reached something physically fundamental. Charge, like matter, is something that's fundamental to everything. Charge is a physical phenomenon inherent to every molecule or atom, whether or not it be positive or negative or neutral, none at all. Electric current is just the measure of how much charge flows in a unit time. So for example, in this circuit, you could take this reference plane here, just measure how much charge flows through it after some number of seconds, and bam, that's your electric current. Okay, so current, often denoted with the symbol I, or I, depending on the scenario. And if you're wondering, the reason we don't use C is because we're about to use C for charge. So current, denoted with the symbol I, has units of amperes, or amps for short. And you'll see that with a symbol A. Charge, denoted with, usually with Q or Q, has units of coulombs. And then time, like you might expect, with a big T or a little t, depending on the scenario. We have units of seconds, denoted S. Sorry, I made a typo here. This is supposed to be a T. And now all I've done here is I'm trying to relate the terminology to our symbols, to our units. And you can see that with these expressions here. So I equals Q over T, that's how you would represent this symbolically. This is supposed to represent physical quantities that you might manipulate in an equation. And if you have any experience with math or physics or engineering thus far, then you know what I'm doing here. And then here I'm just showing the ratio and the unit conversion. So A equals C over S, or amperes is coulombs per second. And I just want to put this here for reference so that you know what I'm talking about in this video or going forward in other videos. And I'm really just trying to lay the baseline here for everything that we're talking about in engineering. So maybe the next thing I should talk about is, well, how do we define current flow through a circuit or a circuit element or conductor? Well, let me start by drawing another quick picture. Let's say you have anything, and I'm being really vague here, a circuit element or a conductor, and this is the physical object, right? And then you pick a point, let's say this reference plane here, or even better, I can just draw it this way. I'm taking this plane and cutting a cross section through this tube or this conductor thing, right? And then let's say that there's charge, flowing in this direction from here to here. And now, like I said, charge doesn't just flow from point A to point B. This would be part of a larger circuit where it would ultimately circulate back to where it started from. But for the sake of argument here, just examine this small section, this one element or conductor, and we're looking at this single cross section here. Now, the cool thing about electricity and electronics and charge and current is that when we analyze circuits, like you'll see in the future, you don't actually have to know what direction the current flows. It sort of turns out to be inconsequential. You'll find that all we do is apply certain physical properties and truths, like the conservation of energy and charge, which I'll talk about later, and the specific direction that the current flows turns out not to matter. You could assign your own physical reality to your circuit and just pick the direction that current flows, and it will turn out to give you the same solution. Now, that's a point that, again, I'll discuss in another video, but I guess what I'm saying is just accept what I'm doing here. We have current, it's flowing, there's a larger circuit. Okay, now given this reference direction of current, or what's really happening is charge is moving, what we have to do is keep a record of how much of each kind of charge crosses this barrier. And what do I mean each kind of charge? Well, like I kind of alluded to earlier, charge can be either positive or negative, right? Or neutral, right? If you're just counting particles, they don't necessarily have to have a charge. But we're just going to say we have some kind of minimum quantization, right? Like whatever the smallest thing is that's flowing through here, we're going to count those. We're going to look at each of those, and whatever their charge is, we count that. We're counting, quantizations of charge here. And so the reason I went off on this whole spiel about how polarity actually doesn't matter, the direction actually doesn't matter, and in the grand scheme of things, we're going to sum everything up and it's going to work out either way. We have to pick a reference direction here, and then we pick a reference charge polarity, as it were. So I'm just going to say that any positive charge that goes in this direction with the arrow counts as a plus, right? And therefore, any positive charge that happens to go the other way, that's minus. And by the same token, because I said that positive charge going with the arrow is a plus, Well, that means that negative charge going with the arrow is minus, and negative charge going against the arrow is a plus. See what I'm saying? We're just counting net change in charge through this cross section. And I know that's kind of semantic, but it's an important one. It's just something to think about. I guess I'm just driving home that point of, I could have said negative charge going with the arrow is plus or whatever, but then you'd have the other implications about what the other three scenarios mean. So just consider that. So by picking that frame of reference, what I've really done is defined a function. I guess I'll call it Q of t, charge with respect to time, crossing this barrier, right? And if you think about the definition of current that I gave before, it's charge per unit time, right? I guess if you have a calculus background, which, by the way, you must have going forward with this, and it'll come on slowly, but you understand the notation that I'm about to write down. And what I want to do is write the definition of current this way. And you see what I've done? So it's you can just describe it as a derivative. It's rate of change of charge, or the time rate of charge is the definition of current. And if you think about everything that I've said here and on the previous page, this is what it's been all along. And people usually regard this as the simplest or most elegant way to describe the phenomenon of current. It's the rate of change of charge, and this will come back as we talk about circuit elements and circuits, circuit behavior and analysis. So while I don't think this is incredibly complicated to understand, because it's not, don't let a derivative spook you, but you should understand this and just fully grasp this, welcome this, accept this, because if you're going to go into electrical engineering, this is entirely the basis for your reality. This is your entire life right here. So, I hope you take this with a smile right now. And by that same token, maybe I should scoot this up a little bit. By that same token, we can write, here it is. We can write charge is the time integration of current with the added knowledge of some reference charge or initial condition. Now again, I don't want you to let calculus scare you off, in particular integral calculus, but this is the type of math that you're going to have to be familiar with in electrical engineering and circuit analysis. Everything is calculus and differential equations. If you can't take a derivative or an integral, you're not going to be able to do circuit analysis, at least at its most fundamental level. You just need to understand these things to have any kind of grasp of the physical processes at play. So, and again, it's not going to be super complicated stuff if you can take one or two derivatives, if you understand what an initial condition is, how to do, single variable calculus and integration, you're going to be okay. But this right here, and in particular, linear algebra and differential equations, that's the core of everything we do in circuits. So got to brush up on that. Maybe I'll do, and hey, this is my first video ever. If it gets to that point where we really start, well, if and when it gets to the point that we're really doing hardcore circuit analysis, or the intro to diffie-qs and circuit analysis, then maybe I'll do a couple videos on it. And I'm thinking, I'm really thinking that what this video or what this series or this channel might become could be me doing examples of solutions to circuit problems, to math problems, to the right way to reason about things, think about things, and approach these problems. And I'm getting way ahead of myself, but I just kind of have this vision of what I could do here. And if people wind up liking this kind of thing, of me helping or looking at stuff like homework problems, then we'll see where it goes. But for now, you should do your best to focus on this. Okay, and on that note, maybe I'll give a quick example right now. So let's check this out. All right, let's do it. Let's say that we have some kind of charge versus time relationship for some cross-section of a circuit, some circuit element. Like any sensible calculus problem, we're going to have an initial condition. So let's say that at time 0, we have this function, charge equals 0. Okay, this is always good. Great starting point when you see this in a math problem. Now let's go and, okay, I'm about to write down a formula that if you've never seen it before, it looks real suspicious. It's kind of scary if you've never worked with an exponential, but I'm sure you have. And the reason I'm doing it is because it exists everywhere. It shows up everywhere. I mean, not just in electrical engineering, mathematics everywhere, but in particular electrical engineering, you will live and die by the exponential, the natural logarithm. So here it is. We're going to do an example in these terms so that you get familiar with this form. So let's just say then that when t is greater than 0, we've got this charge function of time. Okay, now let's remember, and this is all we have to remember here, that I is just dq dt right here, baby. So let's just apply that, right? Like, what does this give us? This is just one iteration of a derivative here, but what it gives you is 200 e to the minus 100t amps, and that's for t greater than 0. Now, let me complete this. I have t. Now just keep track of what I did here. The units went from coulombs to amps, and that's because we moved from charge to current. Remember, the unit that we expressed, the base unit, SI unit for charge, is coulombs. And we took a derivative here. We measured the change in the charge with respect to time, right? So we took this derivative of Q here. We took the time derivative. And if you remember what that does to our units, it creates amps, it creates current. So there we go. This is a super simple example of going from charge to current. It's just a derivative. And if we wanted to go the other way, we would take an integral with the awareness of some initial condition or what charge we start with. And so that's all it is at its core. And if you can do that, I mean, I'm sure most people can do a derivative, but well, in particular, this type of derivative is really easy with an exponential base. But if you just, that's the math here isn't so important as if you just remember the physical process at play here, or the concept of this time derivative, then you're always going to have current, you're always going to have an awareness of what's physically at play, and this is the baseline, this is the foundation for your entire understanding of electricity, electronics, and circuits. So don't forget this, practice this. This is what you focus on in the very beginning in your classes. So on that note, I think I'm gonna end things here. Edit this video, see how long things get when I kind of cut things together. I'm really shooting for, like, I don't know, somewhere between 5 and 15 minutes. I don't know how long I want to make these in general. I'm also, kind of battling with the capacity of my overhead light here. So it's like it's a rechargeable light, but it's not plugged in right now. And the recording's getting kind of long, like raw, unedited. So I don't want to push the light too far. But we'll see. Also, let me know if you want more light or different light in these videos. I can actually make this light a lot brighter, or I could make it dimmer. Who knows? I could introduce other lights from other angles or other themes or whatever. If there's something I can do to make this more clear, if the pen could be darker. I know this is kind of weird with the vertical lines, but hey, I just grabbed my notebook and turned it sideways. So maybe I'll start going with just plain white paper, or maybe I'll find a way to get horizontal lines or something in the future. Anything I can do to improve the quality of these videos, or just the learning experience for whoever's watching this. I really care. So let me know. And with that, I hope you enjoyed. I hope this was helpful, and I hope you stick around for the next video.